Good day, everyone. So today we're going to go over section 13.2, and we're going to run a couple of significance tests for various population means. So what has changed from doing a hypothesis test for P? Well, like I've been telling you, the variable changed. The underlying variable that we collected data for went from categorical now to quantitative. You use a mean, not a proportion, slash percentage to analyze. All right. So it went from categorical to quantitative. All right, so same steps as before. We still have our, say, 5 basic steps. However, the test stat, it'll have a different formula, different conditions, okay? So let's run through the 5 steps really quick. So the parameter that we're going to test a population mean is mu, not the population portion P, all right? And so we went through that, how we would set mu is equal to some value, and in the alternative, mu is greater than, less than, or not equal to some value. And those two values are going to be the same value that you see in the null and the alternative. The value that we see there will be mu sub 0. And we're going to use that in the test statistic formula. Verify conditions or assumptions. Well, we have conditions here. So the good thing is these aren't different from what we saw when creating a confidence interval for mu. All right. So that's a good thing, because you do have different conditions for confidence interval for P and the hypothesis test for P. They're just slightly different. But here, they're the same, the confidence interval and the hypothesis test. So what are they again? The data are obtained either using a random sample or experiment, no extreme outliers, and the sampling distribution of X bar follows a t distribution, also known as an approximately normal distribution. When does that happen? Well, either we need X to be normal, and that's really important when n is less than 30, or n is greater than or equal to 30 and the central limit theorem applies. All right, so then we have to calculate the test statistic. So the test statistic measures how far the sample mean falls from the null hypothesis value, mu sub 0. So in other words, how far X bar, the sample mean, falls from the null value in the null hypothesis, which we're calling mu sub 0. And it's measured by the number of standard errors between them. And so notice what's in the numerator. It's X bar minus the value in the null hypothesis. All right, and then notice what's in the denominator here. The denominator here has what? The standard error, S divided by the square root of n. Remember, that's the standard error of the sampling distribution of X bar. All right, and notice I put a little TS here to stand for test statistic, so we don't mess that up with the critical value. P-value. P-value is a little different here. And so remember, the test statistic is in terms of T, so we cannot use the standard normal table here. Why? Because it's not in terms of Z, the test stat. It's in terms of T. So we have to actually use the T table. Problem is the T table isn't specific enough to give us a very clear-cut answer. All it could do is give us a range, and since it only gives us a range, I'm not going to show you how to use the T table to get a range. Okay, so remember that since we are using the T table, okay, it has degrees of freedom. It's still n minus 1. All right, but what we're going to use to figure out the p-value is StatCrunch. All right, so we'll use StatCrunch to figure out the p-value, and I'll show you when it's actually time to look up a p-value how to do that. Conclusion, same idea, no different than what we did before. If the p-value is less than or equal to alpha, you're going to reject the null. We have strong statistical evidence that the alternative is correct. If the p-value is greater than alpha, do not reject the null. And we do not have strong statistical evidence that HA is correct. So I don't know if I mentioned this before, but the do nots go together. So when you say do not reject the null, we do not have strong evidence. All right. That's just our silly way in statistics of saying we got inconclusive results. We really don't know. All right, so a medical researcher, after several years of general observation of patients, thought it was possible that the mean temperature of all healthy humans is actually less than the 98.6 degrees Fahrenheit that that the medical field typically uses. She takes the temperature of 81 randomly selected healthy humans and finds that their mean temperature is 98.5, standard deviation of 0.3 degrees Fahrenheit. Test your claim at a significance level 0.05. All right, so what's the underlying variable here that she collected data for? Temperature of healthy humans, right? And that's quantitative. So we look at means. What was our sample? So let's see here. It's got to be a sentence or two about the sample. Here it is. She takes the temperature of 81 randomly selected, right? That's N, right? Gets a mean. That must make that X bar. Okay, oop, I didn't get the X bar yet, but that's X bar, and then we have our sample standard deviation of 0.3, but we'll get to that, okay? So N is 81, degrees of freedom is 80. If our sample was 81 healthy humans, that means our population is all healthy humans. We had a sample mean of 98.5, sample standard deviation of 0.3, and we're going to label that as S. Significance level, 0.05. Okay, so step one, state the hypotheses. And so here, H sub A is what? Mu is less than 98.6, right? Because that's what she really wanted to test. That's right there, okay? And then the null hypothesis, 98, mu is equal to 98.6. That means mu sub 0 is 98.6. Conditions, let's confirm those. Took a random sample, okay, check mark, because she randomly selected, okay? Next, no mention of extreme outliers. Of course, we can look at a plot to see that if we had the raw data. And then since n is equal to 81, which is greater than or equal to 30, the central limit there implies, and the sampling distribution of x bar is what? A t-distribution. It's approximately normal. So check mark. We got our three things, and that means we can go ahead and use the formula that I've been showing you. So calculate the test stat. Let me show you the relevant information now. So we got our x bar. I guess I didn't necessarily label that as S, but that's supposed to be an S, not a 5. Okay. And then let's see. We know mu sub 0 is 98.6. We throw that into the formula, all right, and we get a -3 for our test statistic. Since this is in terms of standard errors, we should be able to interpret this. So x bar, our sample mean, is 3 standard errors below, because of the negative sign, below the value in the null hypothesis. Now it's time to calculate the p-value, all right? So the p-value is the area to the left of the test statistic, y to the left, because we have a less than sign here. So we have left-tailed test, 80 degrees of freedom. Our test stat is a -3, all right? So let me show you a picture of the sampling distribution, and this is a sampling distribution of x bar. So notice what's right here in the middle, okay? This 98.6, all right? 98.6 is right in the middle of that sampling distribution. Why? Because we temporarily assume that the null is true. We place it right in the middle, okay? Our x bar ended up right over here, okay? And we got to see the number of standard errors that is away from mu sub 0, okay? So that's why we calculated the test stat. And so here's so this is, again, the sampling distribution of x bar axis, and this is the t distribution. And where are we at? A -3. Okay, so we're 3 standard errors below the value that's in the null. All right, we got to see how rare of an event that is. All right, so what are we going to do? We're not going to go on a t-table. We're actually going to use StatCrunch. Okay, so let's get out of this. And let's get into StatCrunch. And so let me show you. So you go to Stat, you go to Calculators, and you're going to go to the t-distribution this time. And it gives a default of 10 degrees of freedom. It's kind of interesting when you take a look at the different degrees of freedom, what the t looks like. It's kind of crazy at 2 degrees of freedom. At 5, it looks, you know, somewhat more of a bell-shaped kind of distribution. But once you get to about 10 to 15, it starts to look pretty much like a bell-shaped distribution. While at 80, it's going to look very much like a bell-shape and very much looking normal. Not quite normal, but pretty close. So we had a less than. We had a -3 for our test stat. That's what we're going to place here. So 80 degrees of freedom minus -3 for a test stat. Less than. There's our p-value, and I'm going to round it to 4 decimal places. So I got here 0.0018. Looks like 0.0018 for our p-value. And as you can see, it's given us that same area as we had over here. Okay? So let's see here. I got to let my computer catch up. There we go. So we had a p-value of 0.0018. We always compare that to alpha. So the small p-value of 0.0018 provides considerable evidence against the null hypothesis as it is less than, it meaning the p-value, is less than alpha of 0.05. So we're going to go ahead and reject the null. All right, that's a decision regarding the null. And we have strong statistically significant evidence at the 5% significance level that the mean temperature of all healthy humans is less than 98.6 degrees Fahrenheit. And actually, that is the case. There are some researchers, I think, in Michigan, Michigan University, that did this study several years ago, and it's pretty clear that it is less than 98.6. But the medical field just says, you know what, let's just leave it. We've been using that for 180 years, 160 years, something like that, and so let's just kind of keep it, and it's close enough. So they do. All right, let's do a second one. Administrator at the University of Akron is concerned how long it takes students who commute to find a parking space once they get to campus. He wants to test whether it takes more than 300 seconds, meaning 5 minutes, to find a spot once on campus. He randomly selects 100 commuters, and the mean time for them to find a parking spot is 310.4 seconds with a standard deviation of 80. Test the claim at a significance level of 0.05. All right, let's run through this. So the variable is time to park, right? That's quantitative. Thus, we're going to use means to analyze. What's our sample? Let's take a look here. He randomly selects 100 commuters, all right? So that's N. Degrees of freedom is 99. What's our population, all UA commuters? Our sample mean turns out to be, so the mean time to find a spot was 310.4. Okay, there's X bar. Sample standard deviation, again, I don't know why I didn't label it. That's S. All right, that's 80. All right. And so what are those again? Those are the average and the standard deviation for the 100 drivers in our sample. All right, it's just already summarized for us. Significance level is 0.05. So alpha is 0.05. All right, and so I think we got all our background information. So state the hypotheses. We'll start with the alternative. Let's see. So he had a claim here. He wants to test whether it takes more than 300 seconds. Okay, more than 5 minutes. And so that's why we had a greater than. So we have a right tail test. Mu is equal to 300, so mu sub 0 is 300. All right, the conditions. Took a random sample. No mention of extreme outliers in the problem. And since n is equal to 100, which is greater than or equal to 30, the CLT applies, and the sampling distribution is a t distribution. Excuse me. So it's approximately normal. And so we have everything that we need there to use our test statistic formula. Okay. So here's the background information to figure out our test stat. Again, this is S. All right. And then mu sub 0 is equal to 300. We throw it into the formula, and we get 1.30 for our test stat. So what is that saying? X bar is 1.3 standard errors above the value in the null hypothesis. All right, and so the p-value, let's see, we got 99 degrees of freedom, test stat of 1.30, and we have a right tail test. So here is what the sampling distribution of X bar. Okay, there's that axis. All right, and we drew it as a nice bell-shaped curve because the T is bell-shaped. And we had a test, let's say we had an X bar, I should say, I think of around 310. That's about right here. All right, and then when we standardized it, it turned out to be 1.3 for the test statistic. So here is now, I'll have to draw this again. Here's the axis for sampling distribution of X bar, and here's the T distribution. So how many standard errors? We're talking negative 1.3, because this would have been negative 1 here. That's about right. Okay. So this area right over here is the p-value. Okay. And it looks like the p-value turned out to be 0.0983. Well, let's take a look. So we need 99 degrees of freedom and 1.3. All right. 1.3 and 99. Let's check it out. 99, we'll change this to 1.3, and we need greater than. And there we go. What do we got here? We got 0.0983. 0.0983. Yay. Okay. What do we always do? We always compare that to alpha. All right. And go from there. So I'll get back into the presentation. So the p-value of 0.0983 does not provide considerable evidence against the null, that is, as it is greater than alpha. So do not reject the null. Remember, don't accept the null. I'll keep on reminding you that. Meaning, again, the statement in the null and the alternative hypotheses are still plausible. Everything's still on the board, actually. Okay? So remember what was in the null and alternative hypotheses. I'm trying to find it. There we go. So not alone can mu be greater than 300, mu can be equal to 300, mu can be less than 300. Okay? They're still all possible. And if you made a confidence interval, you would see that. You would see that you have the confidence interval would be the lower bound would be somewhere below 300, and the upper bound would be somewhere above 300. Okay, and so you would see that if you made the confidence interval. All right, let's see here. So we do not have, remember the do nots go together, since we said do not reject the null, we do not have strong statistically significant evidence at the 5% significance level at the mean time for all. UA commuting, remember it's not for the 100, it isn't for the sample of 100. Remember, you test parameters, test populations, okay? For all UA commuting students, to find a parking space is greater than 300. So we do not have strong evidence that mu is greater than 300. Okay? So that's what we call a t-test. A t-test when you go ahead and test one population mean. Okay. So last thing, the last problem, the p-value is 0.0983. Let's say, if the problem was two-tailed, if it was two-tailed, so if HA has a not equal to sign, what would we do? We would, since the t distribution is perfectly symmetrical, we would take 0.0983 and multiply it by 2 to get the p-value, because we need both sides, just like we did for the standard normal stuff, okay, just like when we were testing p. So the p-value actually, if we were running a two-tailed test, would have been 0.1966, okay? All right, I think that takes us to the end of our presentation. Thank you for your time.